Here's another exponential equation for us to deal with. This time it's 4 to the x minus 20 times 2 to the x equals negative 100. So one added complication with this equation is we have exponential expressions here with two different bases, along with a constant term over here. But if you think carefully about the fact that we have 2 to the x and then we have 4 to the x, and note that 4 is a power of 2. So I can express these actually with the same base. If we change this 4 right here to 2 squared, so express the 4 as 2 squared, and it's still raised to the x minus 20 times 2 to the x. And then I'm going to also go ahead and move the 100 over to this side of the equation. So plus 100 equals 0. Now, properties of exponents. So this 2 squared to the x, that's equal to 2 to the 2 times x. But if I'm comparing it with the 2 to the x over here, I'm thinking, okay, but then I could also express that as 2 to the x squared. So 2 to the x squared is equal to 2 to the 2x, which is equal to 2 squared to the x. This is still equivalent to that original 4 to the x. But so now I'm going to, because properties of exponents say that I multiply these exponents, well, then it wouldn't matter if I change the order. Multiplication has that commutative property, where it doesn't matter if I write it as, when you multiply 2 times 3 or 3 times 2, it's the same thing. So 2 times x or x times 2, it's the same thing. So this is equivalent. So I'm going to change this first part to 2 to the x squared. And then notice, okay, so we've got 2 to the x squared minus 20 times 2 to the x plus 100. This is now quadratic in form. If you have some quantity squared and then a constant times that same quantity and then a constant term, this is one of those equations that we call quadratic in form. If we want to separate, so if we think of this as an equation with 2 layers to it, and I like to use my hands to illustrate this. If we cover up the 2 to the x's, there's a quadratic equation. So there's a quadratic layer to this equation, but there's also this exponential layer to the equation. So if we're dealing with kind of 2 separate issues in the problem, one way to separate those issues into kind of 2 phases of our solution is to use a u substitution. So suppose we let u replace 2 to the x. So the 2 to the x here and the 2 to the x here, we're just going to replace that with the symbol u. Then this becomes u squared minus 20 times u plus 100 equals 0. So like I said, it lets us tease apart, okay, here's a quadratic equation, I'm going to deal with u, and then I'll deal with the exponential aspect to this later on. So let's deal with the quadratic aspect of this. Let's see, can we factor it? We would want 2 numbers whose product is positive 100 and the sum is negative 20. So how about negative 10 and negative 10? If you multiply negative 10 times negative 10, you get positive 100. And if you add negative 10 plus negative 10, you get negative 20. Here, but it's always nice to double check. So let's see. U squared minus 10u will give me minus 20u plus 100. Looks good. Set each factor equal to 0. Okay, well then we're going to get u equals 10. And wait, I messed up my color scheme. I want u in red. Okay, so you get u minus 10 equals 0, so u equals 10 in both cases. Okay, so that's great. We solved the exponential side of this equation. Now we need to go back and replace u with 2 to the x. So 2 to the x. Now it's time to face the exponential side of this problem. So we need to solve for x in the equation 2 to the x equals 10. I can't express 10 as a power of 2, so I'm going to use logarithms. Use whatever logarithm you like. I'll use natural logarithm this time. Back to natural log. So natural log of 2 to the x equals natural log of 10. Well, the advantage of taking logarithms of both sides, is the green for this, is that you can bring the exponent down in front. So that'll become x times natural log of 2 equals natural log of 10. And so if you divide both sides by natural log of 2, then that'll isolate the x. And so now we've got an exact solution. X equals the natural log of 10 divided by the natural log of 2. In retrospect, common log might have been nice since we have 10 here. But this works just fine.